Welcome, ladies and gentlemen, to Integrated 2 Math. In today's episode, we will be discussing Chapter 8.3.2, which is Ratios of Similarity. And the purpose of this lesson, at the end of the day, will be for you guys to understand how to calculate area and perimeter and use scale factor and ratios to calculate area and perimeter more quickly. So to do this, we're going to we'll be working with three figures here: the rectangles, the triangles, and the trapezoids. And we're going to be determining the ratio of the sides, the perimeters, the ratio of the perimeters, the areas, and then the ratio of areas. And by the time we're done with Part C, I'm hoping you'll be able to come up with a generalization about how ratios of sides to perimeters to areas are all workable in these problems. And so if you haven't done so already, go ahead and print out this page if you have a printer and paste it into your notebook, because it'll just help you move a little bit faster. But if you don't, or if you're unable to print, it's not a big deal. If you could pause the video for a second, copy down the images, copy down the table. This will help organize the information for you a little bit faster. So from here, let's go and just get started with Part A here. Part A is the rectangles. I'm going to first start off by determining the ratio of sides. Well, the ratio of sides is pretty easy because we know that these two figures are similar because the problem told us that they are. So if I'm going to pick one side of the smaller figure, I should probably choose 15 because it's already given to me. And I'm choosing 15 because it has a corresponding side of 25. And in fact, I'm going to move the 15 over a little bit. He has a corresponding side of 25, which means my ratio of sides is 15 to 25. Now, I want to reduce this ratio into 3/5. That will help me see things a little bit better. Now, how does finding the ratio of sides help me? Well, it helps me to find the perimeter. And it helps me to find the perimeter of the larger area, of the larger rectangle. I can find the perimeter of the small rectangle fast because this guy's going to be 6 here, this guy's going to be 15. So if I do 15 plus 15 plus 12, that's 30 plus 12, that is going to be 42. Now from here, I don't know how long this vertical side on the larger rectangle is going to be. I'll go and call him X for now. And I'll go and solve this the way I would solve a similar triangle. Similar triangles and similar rectangles are solved exactly the same way. I'll go ahead and say 6 is to x as, since I'm going from small to large, I'll go 15 is to 25, or as we saw a few seconds ago, 3 is to 5. And I'll go and solve for x that way. So I'm going to get 30 equals 3x, x equals 10. So that's going to be what I punch down into this area, x equals 10. That makes this guy 10 and this guy 25, giving me a grand total perimeter of 70. So the ratio of the perimeters is well laid out for us. It is 42 over 70. And again, I'm sorry, I should move that over a little bit here. 42 over 70. Now I want to reduce that to see if there's any commonalities between the ratio of perimeters and the ratio of the sides. Well, it looks like they both divide into at least 7. So if you divide them into 7, or even greater than that, you can divide them both into 14. You will get 3 over 5 for the ratio of their perimeters. So notice, the ratio of the sides and the ratio of the perimeters in this particular shape are the same. Okay, let's calculate the area of each one. The area of the smaller rectangle here is 6 times 15. That's 90. So I'll go and throw that down right here. 10 times 25 is 250. So the ratio of the areas is 90 over 250. And I can actually reduce that by eliminating the zeros here, giving me 9 over 25. Okay, that's a little bit different. 9 over 25 is not the same as 3 over 5 and 3 over 5. But I'm hoping you'll be able to see some type of relationship between the 3/5 and the 9 over 25. And if you don't see it right now, it's okay. We're going to do 2 more examples, and I think by the time we're done, you'll be able to see a relationship between the ratio of sides and the ratio of perimeters and the ratio of areas. No big deal. Okay, let's go ahead and take a look at the second shape here. We're dealing with 2 triangles here. And luckily, they're 30, 60, 90 right triangles, so we can actually solve them pretty quickly. This guy would be 30, which makes the medium side 6 root 3, and the hypotenuse side 12. Now from here, the hypotenuse here is 4, meaning the short side, which is going to be opposite this 30, is going to be 2, and then making the medium side 2 rad 3. Now for this, I didn't have to do any kind of similarity ratio to find out all the sides, because 30, 60, 90 right triangles, we should be pretty fast at this point. But I probably want to figure out the ratio of sides just to figure out the ratio of sides so I can determine a pattern. So again, the ratio of sides, I'll go and go with one side on the small figure. Let's go with the 4, the hypotenuse here. 4, and then the larger figure, that corresponding side is the hypotenuse of the larger triangle, which is 12. And again, if I can, I will reduce it. I will make that 1/3. Okay, now let's go and take a look at the perimeters of the triangles. So from here, the small triangle is going to be 2, 2 plus 4, so that's going to be 6, plus 2 rad 3. If I look at the perimeter of the large triangle, that's going to be 6 plus 12, so that's going to be 18 plus 6 rad 3. Let's go and take a look at the ratio of perimeters. Now before I do that, if you noticed in the rectangle, the ratio of the sides and the ratio of the perimeters were identical. They were the same. Let's hope it works that way for the triangle. That's going to be 6 plus 2 rad 3 over 18 plus 6 rad 3. Now again, I was hoping that the perimeter ratio and the side ratio would be equal. So the question is, does this nasty looking fraction somehow equal 1/3? Well, let's find out. I'm going to go and take a look at 6. I'm going to do this down here. 6 plus 2 root 3. And what I'm going to do is I'm going to see if they have anything in common. I'm going to factor something out using GCF. We haven't heard that term in a long time. I think a 2 can factor out of there, and that's going to get me 3 plus rad 3. And now I'm going to look at the 18 plus 6 rad 3. So 18 plus 6 rad 3. The GCF here is going to be 6. That gives me 3 plus rad 3. Now remember, that is actually on bottom because my ratio has the 18 on bottom here. So 3 plus rad 3. Notice the 3 plus rad 3s are identical. They can cancel each other out. 2 over 6 is in fact 1/3. So our theory held true. Our ratio of sides and our ratio of perimeters were in fact identical. All right, let's take a look at the area and see if there's any kind of suspicious relationship there. Well, the area is going to be 1/2 base times height, so that's going to be 1/2. The base of the triangle is 2, and then the height of the triangle is 2 rad 3. So those guys are going to cancel each other out, leaving me only with 2 rad 3. The large triangle is going to be 1/2. The base is 6. The height is 6 rad 3. So those guys are going to go away, kind of, leaving me with a 3. 3 times 6 is 18 rad 3. So when I look at the ratio of the areas, 2 rad 3 over 18 rad 3, the rad 3s are going to cancel each other out, giving me 2 over 18, which will reduce into 1/9. So again, take a second, look at the ratio of sides, compare that to the ratio of perimeters, and then compare that to the ratio of areas, and see if you can come up with a relationship. Alright, let's go ahead and take a look at the trapezoid. The trapezoid is going to have some stuff for us to solve. Alright, so from here, we know that the side ratio is going to be 5 over 40. We know that. And that's going to be 1/8 on reduction. We can figure out the perimeter of the smaller figure. That's going to be 5 plus 5 plus 5 is 15 plus 13 is 28. The larger figure, we're going to have to figure out what some of these sides are. So in order to do that, I'm going to go and find a scale factor here. So my scale factor is in fact 1/8, and I'm going to clean up the board here a little bit. That way I can make some room, or actually I can I can work on this side here. I can say 1 is to 8, right? Based on our scale factor, 1 is to 8 as I can say 5 is to x. And I'm going to go and call x this side right here on the what the hypotenuse is of that right triangle looking thing. All right, so from here, I'm going to go ahead and cross multiply. I get x equals 40. So that's what this guy is. He's 40. So I'm going to get 40 here, and it's a regular trapezoid, making him 40. So again, I will go ahead and find out the length of the base down here. So what I'm going to get is I'm going to say, once again, 1 over 8 is equal to, say, I'm going to call this guy, I'll go and call him B. 1 over 8 is equal to 13 over B. Cross multiply, B equals 104, 13 times 8. So this guy here, this B, is equal to 104. Okay, there's going to be quite a bit of stuff being done here on this triangle here. So let me see here. I'll go ahead and clean up the board a little bit, and then we'll solve for the heights of each trapezoid. Give me a second. Now that I've cleaned up the board just a little bit here, let's go and figure out the height of each of these trapezoids. So from here, notice how the entire base is 13. Well, that helps me only in the sense that if the entire base is 13, I want to find out how much this thing is. Because if I can find out how much this thing is right here, this small little slither, then I can figure out using the Pythagorean theorem how much the height is going to be. Well, luckily, it's a regular trapezoid, which means these guys are going to be equidistant apart. And if this piece up here is 5, that only leaves 5 here, making the 13 a 5, leaving 8 units left over to divide evenly between the two triangles. And what that allows me to figure out is it allows me to figure out the height of this trapezoid. Now, because this is a Pythagorean triple, being a 5 on the hypotenuse, a 4 on the base, that leaves only one option for the height, being 3. So what I can do is I can then use similar figures again to figure out the height of the larger trapezoid. So let's do that. I'm going to say 1 is to 8, that's our side scale factor, as 3 is to h. If I cross multiply, h equals 24, and that's what the height of this larger trapezoid is. So why did I do all of that? I did all of that so that I could figure out the perimeter and area of the larger trapezoid. So let's figure out what that is. The perimeter of the larger trapezoid is 40 plus 40 plus 40 plus 104. That all culminates into 224 units. The ratio of the perimeters is going to be 28 over 224, and you guessed it, that actually does reduce into 1/8. Not totally unpredictable, right? Let's talk about what the area of a trapezoid is before we figure out the area of the trapezoid. Now, before you figure the area of the trapezoid, you might actually have a pretty reasonable suspicion if you've been following the pattern, the 3/5 turning into 9 over 25. The 1/3 turning into 1 over 9. Then you might have reasonable suspicion that the 1/8 and the 1/8 will become 1 over none other than 64. Now, if you're wondering how that number happened, that question mark right there, it's okay. We will figure it out. So from here, the area of a trapezoid follows this pattern. It's 1/2 times the height, and then the first base, which will be the bottom thing, plus the second base, which will be the top thing. So if I follow that pattern here, I'm going to say the area is 1/2 height, which in this case, the smaller trapezoid, the height will be 3, and then base 1 plus base 2 will be 13 plus 5. After simplifying all of that, that will actually equal 27. and then 1/2 height, which is 24, base 1 plus base 2, 104 plus 40. That's going to be 1728. 27 over 1728, and actually, believe it or not, that actually reduces into 1 over 64, making this ratio valid. So, what is the pattern that I'm hoping that you are going to see? Well, let's say I have two figures. So, suppose two figures have a scale factor of A over B. Let's figure out the side scale factor, the perimeter scale factor, and then the area scale factor. Well, the side scale factor is going to be A over B. We figured that out. That the ratio of the sides is always one side to the next. Small to large or large to small, it doesn't really matter. We noticed that the perimeter was always the same thing as the sides. And the area scale factor, well, how does the 3 become the 9 while the 5 simultaneously becoming a 25? The 1 stays 1, but the 3 becomes a 9. The 1 stays the 1, and the 8 becomes a 64. That's because you take the scale factor of the side or the perimeter, it doesn't matter which one because they're the same, right? And you square that scale factor. And that right there is the main point of this lesson. So how does this get panned out in actual problems? Let me clean up the board and I will show it to you. Let's go and take a look at one example here. This one's going to be pretty easy. We're just going to figure out the ratio of the sides and the ratio of the perimeters and the ratio of the areas. Now I diagrammed this thing one more time up top here, so if you need to write it down, go ahead and write it down now. The ratio of the sides, go ahead and pick whatever side you want. You know, I think 16 over 24 would be very much doable. So 16 over 24, that would reduce into, if they both divide into 8, they would divide into 2/3. Well, remember, the ratio of the perimeters is going to be the same, because remember, perimeter is just a linear type of model here. Area, however, is going to end up becoming 4 over 9, and that is because 2/3 squared. Now, if you don't believe me, I don't blame you. Let's go and find the areas of each of them. Well, the area of the small rectangle is going to be 160. And the area of the second rectangle is going to be 360. And if I did 160 over 360, that would become 16 over 36. And they both divide into 4. 16 divided by 4 is 4. 36 divided by 4 is 9. That is what we predicted without having to actually find the areas of each of them. So pretty easy problem right there. Let me give you one that's a little bit more challenging. In this next problem, it says two trapezoids are similar. If the scale factor is 3/4 and the area of the smaller trapezoid is 81 centimeters squared, what is the area of the larger trapezoid? Okay. It doesn't really matter what type of trapezoid you want to draw, and actually you don't even have to draw one at all, but I figure the visual might help. This will be the smaller one, and then I'll go and draw the larger one right here. And so it says the scale factor is 3/4. Now, what they are implying here is that this is the side scale factor, which means the area scale factor is going to be 9 over 16. Again, how did I get that? I squared 3/4. I squared it. So how does that help me in finding the area of the larger trapezoid? Without any dimensions, it's going to be really hard to apply that 1/2 height times base 1 plus base 2 formula on this thing. All I know is that this guy is 81, and this guy is some area A, and I don't know what he is. Well, what I do is I set it up exactly as I do with another proportion when I did similar triangles or any kind of similar figure. I'm going to go ahead and say 9 is to 16, which is my scale factor, and because I'm going small to large, my setup on the area scale factor is going to be 81 is to A. And what I'm going to do is I'm going to go and cross multiply, so 9A is equal to, and 81 times 16 is kind of a large number, but if you have a calculator, you'll find that it's going to be 1296. And then if you divide by 9, you'll get 144 as your final answer. Alright, I think that will wrap it up for this episode here. As always, please leave comments and questions in the comments area. And I will have a separate video with a lot more examples of this, and I will see you then.